In this example, we're going to solve an equation containing multiple logarithmic expressions. To start, we know that since our variables are inside those logarithms, we'll need to use our basic property of logarithms, which states that anytime we have log base a of x equal to y, then that's true if and only if we have a raised to the y equal to x. And this property is what allows us to solve an equation containing logarithms using exponential expressions. As we look at this one, we have log base 6 of the quantity x minus 2 plus log base 6 of the quantity x plus 7. So before we can apply this property, we're going to need to use the properties of logarithms to get a single logarithmic expression on that left-hand side. And the property we'll need here is the property that says that anytime we have log base a of some expression m, and we add log base a of some expression n, then that's equivalent to log base a of the product of m and n. So in this problem, we'll apply that property of logarithms first, and then we'll be able to convert this to an exponential equation. So let's start with our original. We see log base 6 of x minus 2 plus log base 6 of x plus 7, which is equal to 2. All right, so to combine those two logarithmic expressions, this left-hand side will become log base 6 of, and then inside here we're going to have x minus 2 times x plus 7. Okay, so at this point, we can see that this product inside here will need to be expanded. We could do that first, or we could convert this right into exponential form. So I'll convert it to exponential, and then I'll expand everything out. So what we'll see then that we're going to be left with is that this x minus 2 times x plus 7 is going to equal, we're going to see that base 6, but now raised to the second power. Okay, and so from here, this equation is just quadratic. So now we no longer have a logarithmic equation. We've converted that to a quadratic one. So our choices for solving, we could expand it fully and then set it equal to 0 and factor it to solve it. We could do expand it fully, set it equal to 0, and use the quadratic formula. We could use the square root property through a more complicated method, but we'll try and factor it if possible. That will be our quickest method. Sometimes it's not possible, but it probably will be in this case. So x squared, and then we've got minus 2x plus 7x, so plus 5x, and then minus 14, and that's all equal to 6 squared, which is going to be 36. So we'll want to set this equation equal to 0. We'll have x squared plus 5x, and that'll be minus 50 when it's set equal to 0. So to factor this, we need two numbers whose product is negative 50 and sum is positive 5. So those two numbers will be positive 10 and negative 5. So we'll have x plus 10 times the quantity x minus 5 when we factor that. Using our zero product principle, this will break down to x plus 10 equals 0, or x minus 5 equals 0. That means that x could be negative 10, or x could be 5. Now, in this case, these are two proposed solutions. It's important that we check these. And what we're checking for is, again, that whether or not these are extraneous solutions, not necessarily that we made an error, although we can check for that as well. So the first thing we want to look at, we'll check that proposed solution of negative 10. So when we try and plug in negative 10, we're going to get log base 6 of negative 10 minus 2 plus log base 6 of negative 10 plus 7, and we would be asking ourselves, is that equal to 2? Now we come up with a problem immediately here, and that is that both this log base 6 of negative 12 and log base 6 of negative 3 are going to be undefined. So negative 10 does not check as a solution. That would be what we'd call an extraneous solution there. So negative 10 is not a solution. It can be tempting to want to apply the properties of logarithms to this to continue checking, but we can't apply any algebra properties because we have expressions that are undefined. So none of those algebra properties would apply. So negative 10 is simply not a solution here. If we want to continue checking that second proposed solution of 5, we'll plug that in, log base 6, and we'll have 5 minus 2 inside there, and plus log base 6 of 5 plus 7, and we're checking, does that equal 2? So this will simplify down to log base 6 of 3 plus log base 6 of 12. And we're again asking ourselves, does that equal 2? So at this point, log base 6 of 3 and log base 6 of 12 don't simplify, but we could, again, use that same property of logarithms we did to solve this equation to show that this is equivalent to log base 6 of 3 times 12. And so now we're asking ourselves, does that equal 2? And what we'll see here then is that this is log base 6 of 36, which we do indeed know to equal 2. So that means then that our solution set contains the number 5 as that proposed solution of 5 checked.